Hi and welcome back. Today we'll be looking at vector subspaces. And if you let's consider any normal vector space, that is V of f. It's a vector space over the field f. And if you have a subset of V, so V is a collection of vectors, U is any subset of that, and if U also forms a vector space over f, that is U itself is a totally contained self-contained vector space, then U is termed as a subspace of f. So U is basically a vector space inside a vector space, that sort of thing. So what are the conditions for any subset U to be termed as a subspace? So subspace is like a promotion, and how do we upgrade U from a subset into a subspace? That's the point. Now note that V is already established as a vector space, and so these 6 rules will be valid obviously. And I want to I want to find out which of the which of these properties, which of the 6 properties are already satisfied in U. So because some properties, the properties that specifically which are marked with the green arrow, since they are satisfied in V already, by the virtue of that, that comes as a free package in U. And so let's look at the closure property. So if U and V are vectors in the original vector space V, U plus V, and A times U for any scalar A, those two are also elements of the original vector space V. But by the virtue of this only, I cannot say that even even U is closed under addition and the scalar multiplication. We cannot say that. That is something we will have to establish separately. But the same cannot be said of commutativity and associativity. So if those two are already established in the original vector space V, though since U is a subset of V, since U is already a subset of V, these things will be valid in U as well, because any element of U is an element in V as well. And if those elements follow these properties in V, it's pretty easy to establish that commutativity and associativity are followed in U as well. And now comes the existence of an identity. Now the 1 times U equals U, I don't think I need to establish that. By the virtue of that being established in V, it also comes as a free package in U, but not the additive identity. That does not exactly come as a free package. We have to establish one thing actually. So if there does exist some sort of additive identity in U, I'll call that 0 dash. So obviously U plus 0 dash will be U for any vector in U. But the point is, this 0 dash, will it be equal to the original 0? Well, the answer is yes, and the proof is that suppose 0 dash is a additive identity vector in U, and 0 dash is not the same as 0. Now look at this. 0 plus 0, U plus 0 dash is U, obviously, by the virtue of it being the additive identity. And now I am taking some properties from V, namely the property of the additive inverse. Now since U is a vector in this U vector is a vector in U, it will also be a vector in the original vector space V. And in that case, there will exist some minus U, that is the additive inverse, will 100% exist in V. And then if I add these two things together, then U plus minus U is going to be 0. That is the 0 from the original vector space V. And now if I add this minus U to both sides, so now the addition is in taking place in the space of the original vector space V. If I add minus U to both sides of this equation, this will reduce to 0. This will also reduce to 0. Now 0 plus 0 dash is the same as 0. But note that 0 is the additive identity, and so anything added to 0 will result in itself, and hence 0 dash is equal to 0. But we said that 0 dash is not equal to 0. That was the wrong assumption clearly. We just proved that 0 dash is 0. And so instead of making the condition that there should exist an separate additive identity, we should say that the original additive identity must be included in U for the fourth condition to be valid. Alright, so this is something we have to establish, that this original 0 vector belongs to U. And now let's look at what do we have to say about the additive inverse. Now note that I'm going to be using a property that -1 times U is the additive inverse of U. This property is actually pretty nice. Now if this is valid in the original vector space V for any vector U, then now I'll consider some vector X in U. Okay, so if I already established the closure property in U, then -1 times X will also be a member of U. Alright, now therefore if minus X, I'm sorry, since -1 times X is actually the additive inverse of X, now this property we have already established, since this comes as a free package from V. Alright, so since this is established, minus X also belongs to U, and U is a subset of V, so that's U is a right, U is a subset of V, and hence the property that I have defined over here, that is -1 times X equals minus X, then if this is valid in V, this stuff should even also be valid in U if we have already established the closure. Alright, and therefore minus U, the additive inverse proved in V, and the closure established in U, these two together will establish that the additive inverse exists in U as well. Alright, so that's why I put a green arrow for this here. This thing uses the property here and also establishment of the closure, and distributivity is also trivial to prove. I mean, this is also inherited from the original vector space V. Alright, so with that, there are two final conditions. I'll summarize this whole thing. There are two final conditions for any subset V to gain the promotion of a subspace. The two final conditions are, one is closure and the other is identity. If U is a subset of V, for U to be a subspace, one, for all X and Y vectors belonging to U, the closure must be established, that is closure under addition. Sorry. So X plus Y must belong to U, and for any A belonging to the field F, A times X also belongs to the subset U. So this is the first condition that we need to establish, closure. The second is that the 0, that is the 0 vector from V must be contained in U. Alright, these are the two conditions for any subset of the original vector space V to be promoted to a subspace of V. Alright, hopefully things were clear. Please go through these things again. Please know where these conditions came from. Okay, don't just memorize these conditions. I mean, if you want, you can do that, but please do understand that where exactly did this even come from. Alright, please go through these again if you don't understand this. Alright, gain a good understanding of where these rules are even coming from. Alright, with that, I'll end the video here. Till next time.